Thank you to Delete Me for supporting PBS. Big things are made of smaller things, and those smaller things are made of smaller things still. That's reductionism in a nutshell. And digging our way to the smallest layer has been one of the primary goals of physics forever. But what if, just before we reach the bottom, we find out that reductionism fails? June is Black Hole Month. At the merch store, we have 2 new black hole merch items for sale. First up is a black hole size comparison desktop and gaming mat. This 32 by 18 inch mat shows a NASA accurate comparison of the supermassive TON 618 black hole compared to the M87 and Cygnus A black holes. And next is the binary black hole orbit t-shirt and sweatshirt that shows how 2 supermassive black hole accretion disks would warp when viewed from near the orbital plane. There's also 10% off everything in the merch store in June. Just use the code BLACKHOLE at checkout. Links in the description. Okay, on to the episode. You are made of cells, and your behaviour can be thought of as the collective behaviour of those cells, whether it's the collective throbbing of cardiac cells behind your heartbeat, or the coordinated firing of neurons behind your subjective experience. We don't need cell biology to describe your pulse rate, we just need a number of beats per minute. And we don't need the neurophysiology of ion channels and action potentials to understand your fear of clowns. Psychology and maybe psychiatry are more useful there. If we go deeper, those heart and brain cells are made of molecules and then atoms, whose interactions can be understood by chemistry without much attention paid to the quantum mechanics at work even deeper down. The universe has layers, roughly sorted according to size, and each layer can be described by its own set of rules or dynamics that we can use without having to know the rules of the layer below. It's pretty convenient that we don't have to do quantum mechanics to understand how people work. And we take this peculiar feature of our universe for granted, but perhaps we shouldn't. It's also convenient that to understand nature, we only need to look to smaller and smaller scales. Understand the smallest, then in principle you've understood the largest. This notion, broadly described as reductionism, has been the cornerstone of much of science and certainly physics since the ancient Greeks. But this too may be an assumption that needs to be questioned. In a recent episode, we talked about the hierarchy problem, the fact that the Higgs particle's small mass doesn't feel natural in the context of this reductionist worldview. Some physicists suggest that this is a strike against reductionism. Others, like Sabina Hossenfelder, who responded to our video with one of her own, contends that it's this notion of naturalness that is misused. But reductionism has been a foundational tenet of physics forever, and naturalness has long been considered an important tool. This video is going to lay down some of the groundwork to give you a solid sense of how these concepts are fundamental to much of physics, which will help us understand why perhaps we should be surprised that these approaches seem to fall apart at the bottom. Let's start by defining some concepts. The idea that big things can be understood in terms of small things is called methodological reductionism. We also have the related concept of theory reductionism that I'll come back to. A few other terms. A level of new dynamics arising from a deeper, smaller layer emerges from or is emergent from that deeper layer. The dynamics, the rules describing the layer, arise from the potentially very different dynamics of its many parts, and those parts don't have emergent dynamics specifically coded in them. If the emergent dynamics can be described without any reference to the underlying dynamics, we say that the emergent system has dynamical independence. Perhaps the simplest example is in thermodynamics, where the positions, momenta of countless particles, literally 10 to the power of 27 independent-ish numerical properties or degrees of freedom in the air in a typical room, are reduced to a few tightly related variables: temperature, pressure, density, and volume for an ideal gas in equilibrium. Or take fluid flow. The Navier-Stokes equations predict the time-dependent behaviour of fluids with incredible accuracy, relating the density, momentum, various stresses, etc. of the fluid with no reference to the nature of the individual particles making up the flow. Their properties are subsumed in the global parameters of the fluid. For example, the maddeningly complex attractive interactions between fluid particles just become a single number, the viscosity. There are plenty of other examples where constituent particles of a system have no knowledge of the emergent dynamics, from the patterns within a murmuration of starlings to skyrmion knots in magnetic dipole arrays. In physics, a theory that works in a particular narrow range of some parameter space is called an effective theory. Newtonian gravity is an effective theory of the more general relativity, with Newton only working in cases of relatively weak gravity. The most prominent type of effective theory in physics is the effective field theory, which is what it sounds like, an effective theory that's also a field theory. That means it describes properties that extend through space, like in fluid dynamics or general relativity or quantum field theories. In an effective field theory, the restriction on validity of that theory is size scale. The component parts of an EFT, be they particles of air or quantum elements of the fabric of space, are small compared to the emergent field. Zoom in close enough and our EFT fails. Things like temperature and viscosity become poorly defined and then meaningless as we enter the realm of individual elements. But zoomed out far enough, the underlying elements are so numerous and so small compared to the EFT scale that this behavior can be averaged over. Their statistics are highly predictive even if the individual elements are not. We say that an EFT integrates over the many degrees of freedom of its underlying elements. We also call this process coarse graining, in that our pixel scale is coarse enough that we can't resolve the underlying elements. At this point, we see ensemble parameters. We find relationships between those parameters. Sometimes those coarse-grained relationships are exquisitely reliable and robust, and the erratic behavior of the underlying parts is no longer needed to predict the system's behavior. This is the dynamical independence that I mentioned. But an effective theory breaks when we move beyond the range of validity. An effective field theory breaks down below a certain size, when the graining is too coarse to capture the increasingly important behavior of the constituent elements of the emergent field. A key requirement for an effective field theory to work is a separation of scales. It has to be big enough compared to its parts that it's not overly sensitive to the random messiness of those parts. Here's an example of pushing an effective theory too far. At the end of the 19th century, physicists were trying to calculate the spectrum produced by hot objects, the blackbody spectrum, the light radiated by particles colliding or vibrating with thermal energy. Based on the assumptions of classical physics, physicists were able to correctly calculate the spectrum produced by hot objects, but only for the low energy, long wavelength end of that spectrum, the infrared or IR in the case of the sun spectrum. When they tried to calculate the short wavelength or ultraviolet UV side, they found that high energy particles contributed far too much intensity, causing the spectrum to brighten indefinitely in that direction. The calculations didn't match reality. This was the so-called ultraviolet catastrophe. It was solved when Max Planck realized that classical physics didn't give a good description of how particles vibrate, and that description got worse the higher the energy. His solution was the birth of quantum mechanics. We've talked about it. The ultraviolet catastrophe resulted from pushing classical mechanics beyond its limit of applicability. By analogy, we often call the limit of an effective theory the UV cutoff. That's the energy where it stops working and we need to transition to a more general, more true description. In this case, the more true description was quantum mechanics. By the way, once we're in the quantum realm, the UV cutoff corresponds both to a maximum energy of validity and to a minimum size, for reasons we've discussed. Let's step back for a second. We can describe the world in terms of effective theories that are emergent from deeper theories. Those deeper theories are, in principle, more fundamental, but in general are themselves also effective theories with their own UV cutoffs. They are coarse grainings of something even deeper. This process of zooming into smaller and more fundamental layers of reality has led us through classical physics to quantum mechanics with an ultimate eye to a single, most fundamental theory. Via this methodological reductionism, we hope to also achieve the other type of reductionism, theory reductionism, which proposes that all effective theories are just different manifestations or special cases of a single underlying master theory, a theory of everything. At least that was the hope. But we saw hints that this program might be in trouble when we looked at the hierarchy problem recently. Let me refresh your memory. Let's go all the way down to the smallest scale at which we have a well-tested field theory. That's the standard model of particle physics, which describes the elementary particles like electrons and quarks in terms of oscillations in the quantum fields. If we accept the premise of theory reductionism, then all of nature should be explainable in the context of that single master theory. The standard model is not that theory because it doesn't include gravity. This makes it an effective field theory, a coarse graining of something deeper. But where is the UV cutoff of the standard model? We might argue that it's at the deepest layer of all. It could be at the size scale of the Planck length at 10 to the power of minus 35 meters. That's around 17 orders of magnitude smaller than the scale of the heaviest of the standard model particles. This is where we know that general relativity and quantum mechanics come into hopeless conflict, and so both of them fail as effective field theories, and we need a theory of quantum gravity. So the quantum gravity scale could be our UV cutoff. But many physicists argue that the cutoff is much closer in energy to the standard model. That makes sense if we take our lead from the ultraviolet catastrophe. Max Planck solved it when he showed that contributions to the blackbody spectrum by high-energy particle oscillations are suppressed in the more true quantum theory. This suppression kicks in at the same energy where the classical theory stops making good predictions. So where does the standard model stop becoming predictive? Some would argue that it's when we try to predict particle masses. Particle masses are a free parameter of the standard model, something measured in labs rather than actually predicted by the theory. But as good reductionists, we expect that the mechanism explaining these masses is hidden in the deeper layer, beneath the standard model's UV cutoff. It's a bit confusing because the mechanics of the standard model, quantum field theory, does actually kind of explain mass, at least in principle. Mass arises from a type of interaction with quantum fields. But in a manner analogous to the ultraviolet catastrophe, particle mass can become very large, even infinite, if you naively add contributions from high energy oscillations in those quantum fields. The main culprit is the Higgs boson, which in turn grants its mass to other elementary particles. Re-watch the last video for the nitty-gritty. But the point here is that the power of the standard model to explain nature appears to fail around the mass of the Higgs boson. Taking their cue from, among other things, the ultraviolet catastrophe, many physicists expected to find new physics close to that mass, physics that would suppress or cancel high energy contributions to the Higgs mass. They did not find that physics. At least the Large Hadron Collider hasn't yet, and it's probed quite a bit deeper than where this physics was supposed to appear in the form of new particles. So, could the mechanics that define the standard model parameters lie much deeper than is accessible to the LHC, or perhaps even to any plausible future accelerator? Could this so-called UV theory only emerge many orders of magnitude in energy and smaller in size than the scale of the standard model, perhaps even at the Planck scale? Many would say that this idea feels unnatural, claiming it requires very precise tuning of the parameters of that UV theory. In an upcoming episode, I'll properly address the fine-tuning argument more rigorously, including whether we should expect the standard model parameters and the UV parameters from which they emerge to be anything other than what they are. Some, like Sabina, thinks we should not. For now, I want to wrap up with an illustration of the strangeness of the situation in terms of size, not energy. What is the typical separation of scales between familiar, dynamically independent levels? Think starling flocks to individual birds, to bird cells, to molecular machinery, to atoms, to the elementary particles of the standard model. We zoom in 2 to 4 orders of magnitude each time. And then we have this chasm that could be up to 17 orders of magnitude between those elementary particles and the deepest possible layer. There's as much difference between the Planck scale to the scale of the Higgs as there is between the atom and the blue whale. Imagine we tried to find out what blue whales are made of and we found no supporting structure for 17 orders of magnitude. No organs, no cells, no molecules, just atoms of blue whale that somehow managed to get their act together to make a cetacean. This is a problem because it gives us a sense that the atoms knew what they were trying to build, which contradicts the whole idea of our methodological reductionism. The parts should not know about the whole. Emergence goes from small to big. This requirement is a bit more nuanced than that. There is feedback between the generating and emerging layers. For example, a cell can't live without its host organism. Molecular machinery requires the stable environment of the cell. Even the lowly quark can only exist in composite particles. There's a feedback between scales. Small generates large, large stabilizes small. But this feedback acts locally, typically each scale directly influencing a layer above and stabilizing a layer below, similar to how the dynamics within each layer is spatially local. Throughout most of nature, this interplay between emergence and stabilizing feedback works when the separation of scales is neither too small nor too large. It's hard to imagine a mechanism for that feedback over the 17 orders of magnitude from the Higgs to the quantum gravity scale. If this is true, it seems like there are really only two broad possible explanations. Now, option one is that the UV theory that ultimately underlies and defines the standard model just is the way it is. It's doing its thing, oblivious to the fact that incredible richness arises many orders of magnitude away in scale. That seems a bit lucky, or finely tuned. We could also invoke the anthropic principle here in that only universes with such a quality end up getting observed by blue whales, presumably. There's a solid case to be made for this, but you do need a ridiculous number of universes to make it work. We'll come back to that sometime. Or option two. Perhaps a type of downward causation or large to small feedback is stronger than the standard reductionist paradigm generally permits. Perhaps the Higgs does tell the lower levels how to get their act together over vast scales to stabilize its mass, or perhaps the Higgs mass is stabilized not from below but rather from above. The general term for this kind of anti-reductionist reversal of influence between the small and the large, the ultraviolet and the infrared, is called UV-IR mixing. And there are some strong motivations to think this might be an answer. We already see UV-IR mixing in one very familiar case, that of gravity, but that's also for another time. In either case, something weird and cool is going on at the bottom of reality, and the clue is in the separation of reality's emergent layers, from blue whales down to the quantum fabric of space-time. Thank you to Delete Me for supporting PBS. Delete Me was built to safeguard its members from data brokers, companies that compile detailed interconnected profiles by scraping public records, mining social media, and purchasing commercial data. These profiles are then sold to various industries, usually without the individuals ever knowing. So, how does Delete Me work? Their platform searches through hundreds of data broker sites, identifies where your information is exposed, and issues official removal requests. It also provides continuous monitoring to quickly catch and address any resurfacing data, as well as protect and prevent things like doxing, harassment, or identity theft. With a family plan, Delete Me extends these protections to linked individuals to help minimize household exposure by disrupting how brokers infer relational connections. You can get 20% off Delete Me consumer or family plans at joindeleteme.com/spacetime with promo code spacetime. There's a link in the description.